Hello, everyone. My name is Yuqi. I'm a PhD student from University of Texas at Austin. Today, I'm happy to present this work with Ahmed Zamzam, Andre Bernstein, who are my internship mentors at Enreal, and Hao Zhu, which is my research advisor at UT Austin. So in this work, we're trying to design topology optimization algorithms in power systems, which can incorporate substation level topology changes. So first of all, let me introduce the definition of the topology optimization. So topology optimization is trying to change the network topology in power transmission system so as to determine the optimal topology to help reduce the generation cost. And it can help effectively relieve congestion in the transmission system. And usually we know that this topology optimization is carried out by switching off the transmission lines. And so the breaker level topology change is usually rarely considered in the previous literature. And in this figure here, it gives a detailed breaker model of the 14-bus system. By changing the status of these circuit breakers, we're able to change the topology of the power systems. And as we know, altering the breaker status in substations can not only lead to line outages, disconnection of generation load, but it can also give rise to bus split events. In these two figures here on the left, it's a simple 3-bus system. And after the bus split, we can find out that this single bus 3 is split into two separate bus 3 and bus 4 here. So this describes a simple example of the bus split. And the motivation of this work is we're trying to design the breaker level switching by incorporating the bus split events, which can further help reduce the generation costs and relieve the network congestions. And for the existing work on this area, it usually have the scalability issue from incorporating all the possible scenarios. And based on our study and simulation in this work, we find out that the reduction in the generation cost can be very attractive. So in the IEEE 118-bus system that we test, by changing only 3 breakers, we're able to achieve the reduction of 19.8%. So we introduced the bus split, and what caused the bus split to happen, we will introduce in detail in this slide. So here we can see that in the middle, we give the detailed circuit breaker model of substation I here. So if we open the breakers in the right circle, after that, the bus K will be only connected to the upper bus bar, bus I, and the other bus J will be only connected to the lower bus bar, bus I prime. So after we do this type of operation on the breaker, this single bus I will be split into two separate bus I and I prime. So this is how we can enable the bus split operations in the operation. And so we record a pre-event and post-event system here. And by utilizing the current reduction, we're able to further reduce the model of the post-event system by moving this generator to its incident bus J. And therefore, we're able to arrive at this equivalent model. So in previous conference version of this work, we have performed a detailed analysis of this topology change. And so the impact of the bus split can be summarized in the following proposition. So for a bus split, it is equivalent to having an opening line L, followed by a power transfer between the two buses. And we're going to use this proposition and conclusion later in our formulation, as is very important. It's a conclusion in the concept bus branch model. And so we mentioned there are going to be power transfer involved in the bus split. So in this slide, we'll discuss the scenarios of the power transfer. So for a generalized model of a single transmission line with two different buses, and each of them has the generator, load, and it can be multiple of them, but here we only give the generator and load. And for the power transfer between these two buses, you can move only the generator, you can move only the load, and you can also move both generator and load. So this will give 3 scenarios from one bus to the other. And reversely, you will find another 3 scenarios from the bus J to bus I. So altogether, they will have 6 scenarios. So we collect all these power transfer scenarios in the matrix called delta L. And on the other direction, it's called delta L prime. So for each column of them, it gives the change of injection. And we further introduce a vector of binary variables called WL, which decides which power transfer that we're going to choose. And in this example, it's 0, 1, 0. So we decide to move the generator only. And so after we introduce all this, we'll go to the final formulation of our topology optimization. So in this model, we are trying to minimize the total generation cost. And after that, this 1B to 1D gives the phase angle limits, generation limits, and line flow limits. After that, these two constraints are called the big M constraints, which enforce the DC power flow when the line is connected. And when the line is disconnected, they become redundant because of this defined large M here. And this 1G will give the limit on the total number of operations that were allowed during the operation. And the 1H gives the network power balance. And 1I is to say that for all these scenarios that we described before, we're only allowed to choose one of the power transfer. And 1J is to say that for a single substation, you're only allowed to make one bus split, at most one bus split. And finally, we also need to constrain the newly introduced line after the bus split. We'll make sure that the line flow on that transmission line is within the limits. So most of the constraints in this optimization problem are linear, except for the 1H and 1K. They're nonlinear because of the multiplication between delta L and WL. So to deal with this bilinearity, we decide to use the McCormick relaxation, which is described here. So normally this relaxation techniques is just a relaxation. It's not exact, but in our problem, because W is a vector of binary variables, so it gives an exact linear reformulation. And so by applying the McCormick relaxation, we can keep all the linear constraints and the linear reformulation here. And after that, this optimization will become is equivalent to this following mixed integer linear program, which can be efficiently solved by commercial solvers like Ruby and Cplex. So in the case study, we first test a small 14-bus system. So here in this configuration, there is line congestion on the line 3 to 4. And after we perform the topology optimization, we decide to open the single bus 3 to 2 separate buses. And after that, there will be no congestion. So to further test the performance of how it can help us reduce the generation cost, we decide to use a larger 118-bus system here, which has 19 generators and 186 transmission lines. So in this table, it gives the results of the switching decisions under the traditional line switching framework and our proposed method here. So we can see that the proposed method provides a more comprehensive switching strategy that can further incorporate bus splitting. So in terms of the total cost, we also provide this figure here, which compares the total generating cost between the line switching and the breaker switching. We can find that the breaker switching can further reduce about 4 to 8% on top of the traditional line switching strategy. And eventually, we also show the computation time of the two framework. In comparison, the computation time for the breaker level topology optimization is on average 28.1% faster. And this is mainly due to the fact that our proposed model will introduce more constraints compared with the line switching. So this will help the solver to search the optimal solution much faster. And for conclusion, in this work, we used equivalent model to give substation level topology optimization under the bus bench model. And to deal with the bilinearity, we further used the McCormick relaxation and attain an tractable solution. And the proposed topology optimization framework can further reduce the generation and line congestions compared with this traditional line switching operations. As for future work, we plan to look into the topology optimization under an increased set of bus split operations. And furthermore, the learning-based framework is also of our interest to address the computational issues caused by the mixed integer program. And that's it for this work. Thank you for listening.